All right, welcome everyone. We'll start in just a moment here on the start of the hour. I think we're there. Welcome. Today's presentation is going to be on IVR and synchronous units, what PRC 19 means for your fleet in 2026, focusing on the NERC compliant standard PRC 19. I'll introduce the team here. My name is Ian Hutt. I'm the Associate Director of Power System Studies here at Commonwealth. And I like to highlight and showcase Madison Stark. She works in our Power System Studies group, has a background in physical design, engineering as well for power systems and substations. And she's here to talk to us today about PRC 19.
Hello all, welcome. Hopefully this will be both fun and educational. So let's go ahead and get started. So PRC 19 is one of the NERC regulations for the bulk electrical system, and it focuses on generating unit coordination and protection. So a couple of learning objectives we're going to try and hit today. Really, it's just understanding the purpose of PRC 19, what it actually requires for generation owners and transmission owners, as well as the coordination elements involved. And then how that coordination applies to both synchronous generation as well as inverter-based generation. There's also an updated version of PRC 19 that's going to be coming out at some point. So we're going to cover some of the changes in that as well. Lots to go over today. It's going to be a lot of information. To kick it off, what is the purpose of PRC 19? What does it do for the bulk electrical system? And the intention of PRC 19 is to verify coordination of the generating unit or synchronous condenser of their regulating controls, limit functions, equipment capabilities, and then their protection system. What it does not do is ensure adequate system protection or require any specific coordination or equipment functions. So what that means is just because you're PRC 19 compliant doesn't mean your system is necessarily adequately protected. What it does is it makes sure that all of the elements that you have in play are properly coordinated for the system. Who does this apply to? Great question. So this applies to two general groups of people, generator owners and transmission owners. So for a unit to fall under PRC 19 requirements, it has to be over 20 MVA capacity. So this is 20 MVA, that's the apparent power, not 20 megawatts, which is a little bit of a different rating. Same thing for synchronous condensers. Any synchronous condenser over 20 MVA falls into this category. Now, if you have dispersed generation, but you have multiple units that are aggregated to over 75 MVA total, that counts as well. With these dispersed units, the coordination actually applies at the individual level rather than at the common bus. Well, it's kind of both, but you have to have individual level coordination as well as common bus level coordination for those aggregate type configurations. And then the last unit that this really applies to is any black start unit. So what is a black start unit? That is a unit that can be turned on without any external power requirements. So a lot of generators require some form of external power source to get the turbine spinning, to get power going, to get the generators excited. But a black start unit is one that's independent, can run independently. And these are important because they're really critical for restoring blackouts. So any black start unit, regardless of size, falls under PRC 19 coordination requirements. Learning objective 1. See, this was an easy one. We got here quickly. Dell, if you could go ahead and populate that first poll.
All right, I will read this out here for everybody, but you can read yourself. Question 1, which of the following facilities require a PRC 19 coordination study, and select all that apply? The first one, a PV array with a common bus voltage control and a gross nameplate rating of 10 MVA, a natural gas generator with a gross nameplate rating of 40 MVA, black start coal generator with a gross nameplate rating of 15 MVA that is material to the restoration plan, a wood-fired generator with a gross nameplate of 18 MVA, and a Type 4 wind turbine inverter-based resource with an aggregate rating of 90 MVA. All right, And we will look to see the selections here on the poll. All right, answers are coming in. And it looks like we got 37 responses. We'll wait a second here for some other responses. All right, as the answers come in, it looks like the selections are the natural gas generator with a 40 MVA rating, the black start coal generator with a 15 MVA rating, and the Type 4 wind turbine with a 90 MVA rating. Seems pretty overwhelming.
That is correct, and it looks like I am an excellent teacher. So these three are of the 5 selections that apply. So the PV array and the wood fire generator are both under that 20 MVA capacity so that they don't apply. And I'm glad that everybody got C as well, which was a little bit of a trick. It's that black start, which is very important to include in the PRC 19. So what are the requirements? This is moving into learning objective 2. So there's 2 main requirements for coordination under PRC 19. So the first regards limiters in the system, and that the requirement is that the limiters operate before the protection system in order to avoid disconnecting the generator unnecessarily. So a limiter is something that's going to curtail or modify the generator's output to keep it within the generator's capabilities. And we want that to operate so that the generator can stay online as much as possible. The second requirement is that the protection systems are set to isolate or de-energize equipment if operating conditions exceed equipment capabilities. So we kind of have a 2-step approach here under PRC 19. The first is that we want to curtail generation if possible to keep the generator up and running safely. The second is that in the event that we can't keep the generator running safely and we're risking equipment damage, then we need to disconnect the generator under the protection system. This regulation does assume steady state operations with a automatic voltage regulator control loop. So that's important because it kind of differentiates it from some of the other regulations a little bit, where we're really focusing on steady state operations for the generator. And this coordination it applies to each applicable facility. So if you have multiple facilities that are connected to a common bus, each of these facilities is required to be coordinated appropriately. You can't have half your site coordinated and half your site uncoordinated. And again, just hitting that order of operations again, we want the limiters to act first to curtail generation to avoid disconnecting the generator. And then in the event that we can't curtail generation, the protection system is what kicks in. The second half of this is the administrative responsibility. So the way the regulation is written, 90 calendar days from any change in these protection or limiting systems or generator capabilities, you have to redo this coordination study and have updated documentation. Even if you don't change anything, you still have to have updated documentation at least every 5 calendar years. So even if you don't change a single thing on your entire site, you still have to do a PRC 19 coordination study every 5 years and keep that documentation on hand. Now, as far as compliance goes, these compliance enforcement efforts fall under the regional entity that the generator belongs to. So the owner is responsible for keeping documentation on hand for 6 years. So that'll go through multiple PRC coordination efforts. In the event that you're found non-compliant, you have to keep it for 6 years or until you fix it, whichever is longer. Hopefully it doesn't take you 6 years to get your generating unit compliant, but it's whichever of those 2 periods is longer. The Compliance Enforcement Authority, or the CEA, will only keep the most up-to-date audit, so you cannot rely on them to keep the documentation that you need to remain compliant. The owner is responsible for keeping that documentation on hand. Learning objective 2, this was also a quick one. Dell, if you go ahead and roll poll 2.
All right, so for poll 2, which of the following accurately describes the purpose of limiters in the context of PRC 19? To increase the reactive power of output during fault conditions, to trip generators off to prevent equipment damage outside of desirable operating conditions, to help generator output more real power in steady state conditions or to modify or curtail the generator operation to avoid shutting off the generator unnecessarily? Select your answer now. All right, 47 responses. Overwhelmingly, we're seeing that to modify or curtail generator operation to avoid shutting off the generator unnecessarily.
Fantastic. That is the intent of limiters under PRC 19. Those two parts really work together to keep generators up and running as well as keep generator operation safe. So great job, everybody. We're going to move into what this looks like for an actual generator now, and we're going to start with synchronous generators. And we're going to do a quick review on synchronous generators. If you're anything like me, you might not have touched it, or you've been working with inverter-based generation, or maybe you're just not that familiar. So let's do a quick review of just what is a synchronous generator and how does this apply to PRC 19. So you have a few major components with a synchronous generator. You have a rotor, that's the part that spins, that's this part right here. On the rotor, you have what's called field windings. The field windings are excited via this DC excitation. And then you have the stator. The stator is the stationary part of the generator. And then on the stator, you have what's called armature windings, also known as stator windings, depending on who you ask. And those are located here. So you have two major inputs as well as a control input to the synchronous generator. You have the mechanical rotation of the rotor. So this rotor is attached to a turbine or a turbine. And there is some mechanical force exerted on the turbine that is causing it to spin. And that spinning of the turbine, which is coupled with the rotor, is then forcing the rotor to spin. You then have the excitation of the field winding. So this DC excitation right here is the electrical input to the system. So this DC excitation on the field windings runs an electrical current through the field windings, and then that electrical current induces a magnetic field, which that magnetic field then induces the current in the armature windings. And as the rotor rotates, that's when we see the generation of electrical power. So our output is three-phase electrical power from these armature windings. So the power generation component, and this is really where you get into the meat and potatoes of what electrical does as opposed to mechanical. A synchronous generator can operate in three different stages: overexcitation, underexcitation, and then unity, which is really kind of an ideal scenario that doesn't happen much. So in overexcitation, the generator is creating both it's creating both watts and VARs. So it's creating real power and reactive power, and it's pushing that all into the grid. So in overexcitation, we're pushing both watts and VARs into the grid. At this point, the generator voltage is going to be higher than the system voltage. So because it's higher, it's able to push those VARs and the wattage into the system. At unity, power factor of 1, the generator is pushing only real power. It is not pushing or consuming reactive power at all. It is only pushing real power into the grid. This is kind of an ideal scenario used in math and theory, but a situation where a generator is only pushing exclusively real power really doesn't happen. And then this other condition that we talk about is underexcitation. And this is when the generator is pulling VARs from the grid. It's absorbing reactive power from the grid. And at this point, the generator terminal voltage is lower than the system voltage. So what you see when it's overexcited is generally the generator is trying to push VARs, it's trying to keep voltage up, keep voltage stable, and provide power. In underexcitation, you generally see that the generator is trying to bring voltage down. The system voltage is too high, and the generator is absorbing reactive power to bring system voltage down. And each of these introduces different strains and limitations on the generator that require protection and coordination via PRC 19. So these two inputs that we have, the mechanical torque and then the field excitation, control different components of the output of the generator. Your mechanical torque is really what controls the wattage, the real power output of the generator. The field excitation, that DC excitation on the field windings, that is what controls your reactive power output. So this is how you're going to manipulate the excitation of your generator via those field windings and that DC excitation, which is important. As far as what actually gets coordinated on the generator, this is where we're getting into how does this operation tie into PRC 19 specifically. You have a few limiters that you're working with. You have your under excitation limiter, your over excitation limiter, and then your volts hertz limiter or your flux. Your volts hertz ratio is really your flux that you're talking about. You have a couple of relays. You have your loss of field relay or relays, depending on the system. And then you have your stator overvoltage relay. And then the capabilities that we're looking to coordinate, we have the generator reactive capabilities, which is really the power output capabilities of the generator, which is your thermal limitations. How much power can it physically produce? And then you have your generator flux capabilities, which relate to the core of the generator. How much current, how much magnetic field can this generator handle? And then you have the steady state stability of the generator, which is how far can you push that rotor angle before it loses synchronization with the grid. The first example of coordination, the most common example of coordination, one of the easier ones to understand, is the PQ plane or the power graph. So this is really the power capabilities of the generator. On your vertical axis, you have reactive power. And on your horizontal axis, you have real power, so VARs and watts. And what we're looking at here is this orange curve is the generator steady state capability. So this is what it can safely do for a sustained period of time. And in this plane, we see how we protect the generator and maintain operation as far as power output capabilities. And what we do is we start here at unity power factor, and then we push out. And that's how we test coordination of our system. So starting here and going up, we're moving into our overexcited territory. We're pushing VARs into the grid. We're supplying a lot of power. So what does this look like? Well, the first thing we're going to hit is our generator capability. That's good. Steady state capability, we can sustain this indefinitely. The next thing we're going to hit is our overexcitation limiter. Also good. What that means is that as we exceed our generator's capabilities, the limiter is going to kind of push it back down to maintain a stable steady state operation. The reason why you see the limiter on the far side of the capabilities is in fault conditions, this generator needs to be able to push additional power. So having this limiter just outside those capabilities means that the generator can respond in fault conditions to help restore stability to the grid. Also highlights one of the limitations of this depiction. You can't see the time element. So we can see as far as like actual power goes, but this limiter has a time constraint on it. So it's not going to let the generator just sit here outside of its capabilities indefinitely, even though it's what it looks like on this graph. So there's a time element that's captured in other parts of coordination. And then once we pass the limiter, we hit the trip. And that's good. We have exceeded the limiter's capabilities. Now we're going to trip and protect the generator. It's exactly what we want to see. Now, when we move into the under excitation portion, the first thing we're going to hit is the under excitation limiter. Good. And you might ask, well, why is that one inside the generator's capabilities? And we'll get to that in a second. The next thing we're going to hit is this loss of field zone 2 relay. This is a slow acting time-based relay. It's going to give the generator a second to correct itself, get back to this limit, and then it's going to trip to protect the generator. We then hit this under excitation capability curve for the generator. And then we hit our loss of field zone 1 relay. This is a fast acting relay. It's going to trip instantaneously. And the reason why is this steady state stability limit here. Now, when you exceed the generator's thermal capabilities short term, generator is probably going to be fine. It has the ability to sustain outside operations for a little bit. It's called thermal inertia. Now, this steady state stability limit, breaking synchronization, the generator has no ability to withstand a deviation in that regard. If it becomes unsynchronized, that's going to cause instant damage to the generator and can be incredibly devastating. So that's why all of this is on the inner side of that, because we're trying to create a buffer with that steady state stability limit. What you see over here, These thermal capabilities are generally more conservative than the stability limits. It's that way on purpose. One of these is much more devastating than the other, so it's important to protect for the most devastating event. So this is a quick case study of, these were just default settings that we saw on one and how to properly coordinate them. So I highlighted in red the parts that are like, ooh, maybe this isn't exactly what we're looking for. And the biggest thing is, one, we have these two relays all the way inside the generator capabilities. So these are going to kick the generator offline when it does not need to be kicked offline. So we're going to lose power for no reason. Not what we're looking for with PRC 19. And then this limiter down here, which we're really hoping would be used to curtail power, it's actually not doing anything. The generator is going to burn up far before it hits this under excitation limiter. So not what we're looking for. Now over on this right side, we see that corrected, where the first thing we hit coming out from unity power factor is this limiter, great. Then we hit our zone 2 relay, perfect. It's going to be slower acting, give the generator time to respond. We hit our thermal capabilities, okay. And then our zone 1 relay, this is our instantaneous catastrophic event based relay that's going to trip and protect everything that it can. So this is kind of the sister or the cousin to the power graph. This is the impedance plane or the RX plane. And impedance and power have kind of an inverse relationship, where as impedance lowers, the generator can push more power, and as impedance raises, the generator can push less power. So this really shows relay behavior in terms of system impedance, which is important because relays are programmed in the impedance domain. They're programmed to take the voltage and current that they can measure and then calculate impedance. And based on the impedance, they have their designated trip conditions. So this can account for scenarios where the generator might be operating within the defined power constraints, but because of things like changing fault impedance or distance problems that you see between like distance type relays, those things have different impedance profiles, even though they have the same power profile. So having the impedance coordination gives you a deeper insight into exactly how those relays are programmed and make sure that you're not missing any corner cases or nuanced scenarios where you might be getting either trips that you don't want, or you might not be tripping in a situation where you need to trip. So this is kind of just a sister to that power graph. It gives you a lot of insight into exactly how those relay margins are developed and ensures coordination. Quick case study. This is the same example from before, where we see kind of the exact inverse of the power graph. And here we have our under excitation limiters way on the inside, unfortunately not protecting anything. For the impedance plane, you work from the outside in. So you start all the way out here. What do we hit first? Zone 2 relay, zone 1 relay. Oh my goodness, instantaneous trip. And then we hit our reactive power capabilities. And then we hit our limiter all the way in here. And that's really not what we want to see. What we want to see over here is much better. So as we come from the outside in, the first thing we hit is this limiter, perfect, going to curtail operations. Then we hit our zone 2 slow acting relay, perfect. Then we hit our generator capabilities, and then we hit our zone 1 relay instantaneous trip. So that's a lot more of what we're looking for in the coordination element to protect the generator. Another option for coordination that you can see is an inverse time characteristic plot. For current specifically, they're also called a TCC or a time current curve. And what this does is it allows you to coordinate your limiters specifically with the thermal limits of your field windings. So what we're looking for here is coordination moving from your corner over here outwards. And this is how you check your coordination. So again, we want to hit that limiter first. We always want to hit the limiter first. So as we move out, the first thing we hit is this limiter. Perfect. This is our overexcitation limiter. Great. And then the next thing we hit is our phase relays. Fantastic. And then the next thing we hit is our field winding limit. So the field winding limit is a little different than the overall thermal limit of the generator, but this is an acceptable coordination metric for a synchronous generator coordination. So one thing this also accounts for that you don't see on the power plot is time. So as time increases, even at a lower percent of field current, you're still going to hit those limits and those trips. So it is time protected for lower deviations, but those require a lot longer for the system to trip. One of the challenges here is to minimize that margin between your limiter, your protection, and then your field winding limits, because you want to keep your generator up as much as possible. That's the best case scenario for the grid, for your generator, for everybody involved, is you really want to keep pushing power. But you also want to protect your generator. So it's kind of a balance of how do you minimize downtime while ensuring that you have the appropriate safety margin. And this is where it's a little bit of art as well as science, because there's not necessarily, every situation is going to be different. You have to account for your relay timing, you have to account for trip timing, and all of these other factors when you're looking at this timing margin. So it's going to be different for every system, but there are standard guidelines and criteria for what this margin should look like overall. The last element that we'll touch on for synchronous generators is called flux coordination. So this is your volt-hertz coordination for your system. So what is flux? Great question. They have entire courses on it. The purpose of this, though, the flux involves the changing magnetic field. So the flux is the measure of the changing magnetic field. So the magnetic field that's induced by the field windings as the rotor turns generates a magnetic field. And we're measuring that indirectly through the volt-hertz measurement. And the core of the generator, if the magnetic field increases to a certain point, or that flux increases to a certain point, the core of the generator will saturate. And that can create thermal runaway in the generator, which is devastating. Don't want that to happen. So we have a maximum volt-hertz ratio, which helps prevent that saturation. There is a level of that volt-hertz ratio where the generator loses efficiency and doesn't operate very well, but it doesn't really pose a risk for equipment damage, so we don't really worry about protecting for that. We really just worry about that maximum threshold to prevent saturation. So what we see on this volt-hertz graph, and you'll notice it looks very similar to a time current curve or an inverse time plot. General, you have your time on your horizontal axis, and then you have your percentage volt-hertz ratio on your horizontal or your vertical axis, sorry. And again, same thing, we're going to work all the way from this corner down here, and we're going to bump our way out to make sure that our elements are coordinated. So we want to hit that limiter first. Perfect. That's what we hit. Well, actually, we hit this alarm. Great. Not everyone has an alarm, not required. But we hit this limiter, which is what we want to see. And then we hit our relay trip. Perfect. And then we hit the generator limitation for that volt-hertz ratio. This particular example has some additional elements that are coordinated for and planned for, which are the UAT, the unit auxiliary transformer, and then the GSU, which is the generator step-up transformer. This is what connects the generator to the grid, and this is what provides power to the generator equipment. So your relays and your exciter and all of these things are powered by the unit auxiliary transformer. So great things to protect for, especially in the event that one of them had a lower flux tolerance than the generator. This would be a great thing to show coordination for. However, it is not required. Great thing to do, not required. All right, so that kind of wraps up what we cover for synchronous generators. Dell, if you want to roll poll 3. I know there was a lot of information.
Yep. Question 3. Synchronous generators can have which of the following as evidence of coordination under PRC 19-02? A PQ graph with relays and limiters, an RX graph with relays and limiters, a flux graph with relay, limiter, and generator capability, an inverse time plot with relays and winding thermal limits. Vote now. All of the above is also an option. So it seems overwhelmingly, with 44 responses, that all of the above is the response.
Fantastic. All of the above is the response. All 4 of these are great examples of ways that you can demonstrate coordination with asynchronous generator. There are other examples as well. you can also show calculations, you can show other means of coordination, but these are some of the most common and some of the easiest to really like see and plan for that coordination for a synchronous generator. All right, moving into inverter-based generation. Quick touch on what is an inverter, what does it do? At its core, an inverter converts DC power to AC power. So where does that come into play? With a lot of your DC-based generation. So you see it with PV arrays, which are DC. You can see it with battery plants, which are not technically generation, but batteries operate in DC, so they all have inverters to connect them to the grid. You see it in some types of wind turbines. Type 3 and type 4 wind turbines involve inverters, although they actually have converters, but they have an inverter connecting them to the grid. So inverters are what's considered current limited devices. They have a defined amount of current that they can output, generally rated somewhere between 1.1 and 1.5 per unit of their nameplate rated capacity. If you're not familiar with the per unit system, what that means is it's like 110% to 150% of their rated capacity. So a synchronous generator can output 3 to 6 times their nameplate rated capacity for current, but inverters cannot do that. So that's a huge limiting factor on an inverter that has to be planned for. The apparent power output for an inverter is not controlled by excitation and rotating machine type inputs. It's controlled by software programmed inside the inverter itself. So this reactive power capability for the generator is bounded by these apparent power limits, which are controlled by the internal controls, the internal software of the inverter. What you see over here on the right, this is a reactive power, active power, so a power capabilities curve for an inverter. This is just a sample. They generally follow this general shape, where they have a rounded top, and then they have kind of these steep cutoffs on either side that are their reactive power limits. These inverters do not have an excitation system, and they do not have the limiters like you see with a synchronous generator. So their ride-through capabilities and their limiters are all controlled by their internal controls, their internal programming. The external protection that you see, similar to a synchronous generator, acts in very much the same way, where it's a backstop. When operating conditions exceed the programmed capabilities, then these protection systems are going to act to protect all the equipment in the system. Now, I don't know if you caught this, but when we went over the language of PRC 19, a lot of that verbiage really was geared towards synchronous generators. So the coordination elements that are described in PRC 19 for inverter-based generation are very limited. It's kind of constrained to over-under voltage protection, the inverter overcurrent limits and protection, and then you can include downstream flux protection for things like your generator step-up transformers, if you have any other auxiliary transformers in the system or anything like that. So the first thing we're going to touch on is voltage coordination. So voltage coordination when you're doing distributed type generation, so you have multiple PV arrays that are connected at one point of interconnection or POI, you generally are evaluating the voltage at the POI and then backtracking it through the system to test the inverter capabilities. So what does this look like as far as actual coordination? So similarly to a synchronous generator, you're going to start in this middle at this 1 per unit voltage. This is your baseline ideal operating conditions. And then you kind of work your way out. So the first things that you want to hit for an inverter are your voltage ride-through requirements. So these are designated requirements that your inverter has to be able to ride through. These are voltage events. The voltage in the system goes high, the voltage in the system goes low. The inverter has to be able to continue to produce, well, not produce, but to continue to push power in these events. So here, when we go up, we see this high voltage ride-through line with no intersection. Fantastic. The next thing we want to see is the inverter protection itself. This is that inverter internal control that's limiting the inverter's behavior. And that's the next thing we want to see. Perfect. And then outside of that, we want to see our feeder protection. This is our system protection. This is our big overarching protection. That we want that to be the last thing to go, because that's kind of plant shutdown criteria. That's going to stop all connection to the grid. That's what's going to shut our plant down. And we want that to be the last thing to act. So here we see no intersection. That's our last thing. Great. On the high side, this is appropriately coordinated. Now, if we go down to our undervoltage scenarios, where we want to see the same thing. Here we have our low voltage ride through. That's this orange line. The next thing we want to see is this inverter under voltage. This is the inverter's internal controls. Perfect. That's the next thing we want to see. Amazing. And then the last thing we want to see is that overhead system protection, which is the feeder under voltage, which is right here. So perfect. Looks like the system is appropriately coordinated. An interesting note, because of the way PRC 19 is written right now, the voltage requirements correspond very closely, if not identically, to the ride-through requirements in PRC 24 and PRC 29. PRC 24 and 29 do not take the place of PRC 19. These are still separate requirements, but there is a lot of overlap in what those requirements look like right now. So it's just an interesting thing. PRC 24 and 29 are in relation to the voltage and frequency ride-through requirements for generating systems. The second part of this for inverters is the overcurrent coordination. And the big thing that we want to see generally at POI again is that the protection system is not impeding the resource output capability. So we want to see that inverter can output its full profile, basically, of the current that it can output. So if we look at this graph over here on the right, for reference, this red highlighted area is the resource capability for this particular inverter. And what we see is it has a 120% overage, that's within that 1.1 to 1.5 per unit, that it can sustain for 10 seconds. So that full overage has to be outside of the protection system, because we want that to be able to be fully pushed through. And that's exactly what we see. So these are the feeder relays and then the upstream relay from them. And these feeder relays are appropriately coordinated to not impede the inverter's internal control system and output capability. So in accommodating this overage, this is what accommodates the ride-through requirements and fault requirements of the inverter systems. This right here is another time current curve, inverse time plot, a couple different names. This is the most common way to show coordination for inverters for PRC 19 for the overcurrent coordination element. You can show this on a power plot or an impedance plot. This is much easier and it shows the coordination a little bit better. Of note, this also corresponds to another PRC regulation, which is PRC 25. PRC really is targeting protection system coordination during fluctuations, including overcurrent scenarios. So where that comes in is this is the inverter internal controls have to be coordinated with the system protection, which is the same thing that you see for PRC 19, because you want your system capabilities, which are tied to those internal controls, coordinated with the system protection capabilities. So a lot of overlap there for the inverters. This is just another example of what a time current curve for, and this is a converter type resource, which is, it's an inverter with an extra step. But that coordination that you're looking for is the same general thing, where you're coming from the left over to the right, and you want to hit your full load current capabilities first before you hit your protection system. That's exactly what we see. So we hit our full load current right here, followed by the protection for that particular element of the wind turbine. This is a type 3 wind turbine. So it has both the converter portion as well as the stator portion, which just outputs straight AC power, which is also similarly coordinated. And then this graph actually goes the next step further, where it includes these. This is the transformer damage curve, the switchgear damage curve, and then the stator damage curve for the AC portion of the wind turbine. So how I talked about incorporating the flux protection or the thermal limitations of downstream equipments. This is another way that you can show coordination with downstream elements and demonstrate that the system is appropriately protected. Just hitting on this one more time. So the current limiting controls, so this right here, which limits the current output, is really what's taking the place of those limiters that we saw on the synchronous generators. And then the external protection functions almost identically for both the synchronous and the inverter-based generation. So this is poll 4. Dell, if you could roll it.
All right. So this is a fill in the blank. Question 4. Inverter-based resources do not have blank or blank, so they use blank to control power output. Turbines, stators, internal controls, exciters, limiters, internal controls. Current limits, power limits, rotors, exciters, rotors, and standalone relays. Choose one of the 4. All responses are coming in, 14 so far, 25. Give it just a minute here till we get up in the 30s, 32. 40 responses. Okay, so we're a little split. So turbines, stators, internal controls at 33%, exciters, limiters, internal controls at 44, exciters, rotors, and standalone relays at 18.
So this one was a little tricky, so great job. The correct answer is B. So inverter-based resources do not have exciters, limiters, so they use internal controls to control their power output. Now, what are we looking for in this correct answer that maybe is showing like a little bit different from what the other answers potentially could have been? So inverter-based resources do not have turbines or stators. Sometimes, but some wind turbines are considered inverter-based resources, but they still have turbines. So that's a little bit of a trick. Sorry for tricking you. I didn't actually cover that. So good job if you got it. And then as far as the standalone relays versus internal controls, standalone relays don't control power output. They trip power output. They shut off power output. So that's a big difference between the internal controls versus standalone relays in the system. Is your internal controls are what's going to determine how much and what kind of power is coming out of this relay or is coming out of the inverter, where a standalone relay is more so looking for operating conditions now exceed what we're looking for, we're going to trip. So those are a little bit of a nuance between the internal controls versus standalone relays and some of the nuances between turbines specifically as far as exciters, limiters, etc. So what are the coming changes? So of note, PRC 19-3 has not been approved for official publication. It doesn't have a date for official publication, but it has gone through at this point a few rounds of comments and feedback. So I think it's pretty close to the final version. And these are some of the big changes that we see in PRC 19.3. The biggest one, I think personally, is there is a huge shift towards including inverter-based resources in the requirements language. So they now have specific, or they will have specific requirements for inverter-based resources, which include how does a power plant control system for distributed generation type work, and how is that coordination supposed to look for this regulation, and then as well as for the distributed generation where the individual protections are what's included in the system, what does that requirement look like, and what is that coordination supposed to look like? It also expands the protection system definition to include both relays, so standalone relays outside of the generator, as well as the embedded protection in the control system. So within the exciter, there's some embedded protection. Within the inverters themselves, there's some embedded protection. So it kind of clarifies what protection system actually means and which things are included in the protection system versus other components of the system. It also, and this is a big one, is proposed to take out the periodic renewal requirement. So basically, if you don't change anything, you don't have to redo PRC 19 coordination. There's that 5-year requirement goes away, and it basically just turns into a 90 calendar days of any system changes. So if you have a generator that's humming and you're coordinated and everything's good, great. Don't have to think about it. But if you change anything, you still have to think about it and do that updated coordination. It also clarifies some of the points about what the required control coordination involves and what evidence there is. So this specific example, they're removing the steady state stability limit portion. Why that matters is they got a lot of feedback from generator operators that this steady state stability limit that you were calculating was kind of a manually calculated thing. The steady state stability limit is very dependent on what the grid is doing as far as like frequency and voltage, and compared to what the generator is doing. So because the grid itself and you have voltage controls outside of the generator, calculating this steady state stability limit to put on a single graph for coordination isn't really helpful or accurate in determining coordination. It's kind of something that like changes and has flux in it and varies. So they got feedback from generators. I was like, hey, the steady state stability limit requirement, it's not good, doesn't work, not helpful. And so they actually took that out. And this is just my little plug that if there's something wrong with the regulation or it doesn't make sense to you, say something and maybe it'll get incorporated. So that's another big change that you saw. This is a quick overview. It's not actually a very long regulation, but these are some of the big changes that we saw. So last question, Del, can you roll poll number 5?
All right, question is, PRC 19003 does not include which of the following is an expected change: residential PV array coordination requirements, inverter-based resource coordination requirements, removal of steady state limits as a coordination metric, and clarification on protection system definitions and inclusions. Responses coming in, 24, 34, overwhelmingly residential PV array coordination requirements.
Yay! The PRC regulations, including PRC 19, including new versions of PRC 19, are exclusively based on utility scale providers connected to the bulk electrical system. Residential PV arrays are not now or probably at any point in the near future going to be required to do this level of coordination. So that is a great point on the emphasis of these regulations, which is utility scale power, not residential. So if you have a solar array, don't worry about it. You don't have to publish a PRC 19 report. So that kind of wraps up everything that I had. Are there any questions that we have?
So if you have questions, please post them in the chat. We will read those off and then we will respond accordingly. We will wrap up at the top of the hour. So any questions that don't get addressed, we will work with you to address them after the call if they exist. So if you have any questions, please post them in the chat.
I apparently did an amazing job.
So one thing I'll mention just while we're waiting for questions to come in, I mean, PRC 19 has been a big thing for quite a while. We're seeing more and more requests for PRC 19 studies with our work in renewables. So with the big boom of solar that's kind of hitting all areas of the country and every ISO market and every conventional market, you know, this PRC 19 requirement is there. It's needed usually for new construction builds as well as the cycling 5-year requirement as well. So first question that came in from Bernard, will this recording be published for our reference? Thanks. Del, did you want to speak to the ability to get to this presentation after the fact?
Yeah, so once this webinar is over and the video is processed, we will be sending out a recording that you can watch on demand. And also in the next week, it will be posted on our Commonwealth YouTube page for you to watch at a later date. But yeah, you should be receiving a link to a rewatch in your email later today.
And I don't want to butcher your name, but we'll go with this one. So how do you read the last time current curve?
Great question. So what we're looking at for this last time current curve, so this is for a little bit more explanation on what exactly we're looking at here. This is a type 3 wind turbine generator. So a type 3 wind turbine generator outputs some power via a converter and some power via a traditional generator type connection. So that's why you have 2 full load currents and then 2 protection curves. So this first curve over here, and again, we have time and seconds on your left-hand side, and then you have current in amps on your horizontal axis. So as we read from left to right, this is our current increasing, and as we read from bottom to top, this is our time increasing. So as current increases, the first thing we're going to hit is our converter full load current. So this is the maximum full load current that the converter can output. And then the next thing we're going to hit is this converter main breaker. So this is the main protection for this converter. And what that means basically is that this main breaker is not impeding the converter's function or internal ability to output current. So that's the coordination that we're looking to see for a converter. The next thing that we're going to hit is this stator full load current and then this stator main breaker. So this is the maximum full load current, steady state operations, that the stator portion of the wind turbine can output. What that basically means is that these 2 elements, this coordination element right here and this coordination element right here, the yellow and the red, they're not really correlated at all. They're like 2 separate elements that require separate coordination. And then what we see over here all the way on the right side, these are basically your substation elements that connect both of these points to the main grid. So we have our, well, actually, I lied. This is the stator thermal curve. So this is the thermal limitations that this red breaker is protecting. This right here is the step-up transformer. So that's taking the aggregate current from both of these components and then pushing that out to the grid. And this is our switchgear, which is where both of these currents are connecting to. And then they're going to the step-up transformer and then going out to the grid. So these are like your substation type elements on the POI, the point of your connection side of the house. And then these are our 2 generating elements. Well, this right here, and then this right here are the 2 generating elements for the type 3 wind turbine generator. So hopefully that clears it up a little bit.
Yeah, very good. One more question was asking about CEUs and PDHs. We do offer a PDH here. Dell, do you want to state the email that they can send a request in for PDHs?
Yes, we will be, if you've watched this webinar, please send an email. I'll type it in the chat to marketing@cai-engr.com. And in the subject line, just put PDH and request that you are looking for a PDH for this course, and we'll get that to you in the next few days.
Yeah, it's like PDH, PRC 19. That would be all we need. Yeah, so. All right, perfect. Sounds good. Still have the chat open for any additional questions. Again, just kind of talking high level here while we're waiting for questions to come in is we've been focused very much on PRC 19 as part of this discussion. There are other PRC requirements for generators. Likely if this applies to you, there are these others would as well. Those, for example, are PRC 24/29. We're moving into 29 now. That's now in effect. PRC 25, PRC 27. So as we go forward, we'll very likely have some additional webinars that kind of talk about those PRC requirements in more depth. So just a couple of things to be aware of as you're moving in, especially if you're developing new projects. Some other requirements that may affect you as well as things like MOD 32. Now, modeling requirements are also part of the same kind of package, and we see those quite often for our renewable projects as well.
Mike had a question in the Q&A portion. So as far as adding time between initiation of trip and breaker opening, that kind of like margin that you're looking for there. So not necessarily specified in PRC 19, but kind of an element of all protection and coordination when you're doing these types of efforts. So one of the things that you can do, which I took all the identifying details out, so it's not specifically labeled in here, but one of the things that you can do is you can calculate out what that time looks like between your relay response time, your opening time, your margin of error that you include in both of those, and all your other little bits that add up. And then you create basically a project margin for your site. And that time margin is then what you determine. So you can see this red line between these two relays. Typically, we would have a time label on that specifying that this time does include that time opening or the response time, or if you have like an error margin in your CTs where you have a 3 or 5% current reading margin, that also can be included in this. And all of that is kind of what's built into your margin when you're coordinating elements. So while you don't necessarily have to put like a separate curve in, you can include that in your reports or in your calculations of how you got to the required margin that you got to, not just throwing darts at a wall, picking a number out of a hat. And then those calculations basically support or justify why the margin between your protective elements is sufficient. And then on a TCC, you can show the time margin via like, these are like crosshairs that show time margin, or you can show current margin here. That's another one that we also show sometimes to demonstrate that level of coordination. That answers your
And a couple
question.
things, yeah, a couple good things to mention on there too is this is this is a log scale curve. So it looks like we're kind of tight, around where that red horizontal line is. But mind you, that's in the seconds range. So there is a lot of margin there. Once we get down towards the bottom of the curve, now we're talking cycles. It's much faster. But Madison's absolutely correct, is that, we try to make sure that there's margin between our protected devices. There's art and science here too. There's trade-offs sometimes that must be exercised, but in general, assuming that we have, say, like a 3-cycle breaker, we want to count for, relay operating time. We want to count for lockout time, breaker operating time, and some additional margin to account for some unknowns. Things like accuracy, saturation can affect, relay operations. We want to make sure that we cover those as well to give us the best chance for coordination and success when we're looking at coordination plots. All right, I don't see any additional questions, so I just wanted to say thank you for everyone who attended today. I really appreciate your participation. Please reach out for your PDHs if you're looking for that. And we will see you next month. We have another presentation that'll be rolling out with an invite here for February. So we'll be talking a bit about DERs next time. So thank you very much, and we'll be in touch. Have a great day.
Thanks, everybody.